So here's what I want the students to see, whether it's in the YouTube video or you do it or you show me doing it. There's a noticeable delay between the instant the can enters the water and the instant the can collapses. So I tell my students that the can actually undergoes two processes. One, isochoric, as the air goes from hot to cold. As the air goes from hot to cold, that's an isochoric process. The can has not yet changed its volume. Then an isothermal compression, the can is already cold, now the can collapses. An isothermal compression, first an isochoric cooling, constant volume cooling, then an isothermal constant volume compression as the can crushes. Okay, I asked them to draw both processes on a PV diagram, on a PT diagram, and on a VT diagram. I asked my students to make these simplifying assumptions that the can starts at 350 milliliters of volume, 1 atmosphere pressure, and 540 Kelvin temperature. And I asked them to pretend that the can ends with half its volume and half the temperature. And then what happens? The pressure is the same at the very start, the very end. It is 1 atmosphere because it is the outside air pushing on the can. Okay, so here's what I give them. I give them a pressure volume diagram with 1 atmosphere and a full can labeled as 2 special lines. Pressure temperature diagram with 1 atmosphere marked and 270 and 540. That dot is the starting point before the can is crushed, so is that dot. Volume is a full can volume, and you have 270 and 540 kelvins there as well. So all 3 of these dots are the initial state of the can before it goes in the water. Here's the correct answers. The pressure reduces as the temperature reduces, then the pressure goes back to 1 atmosphere as the can is crushed and the volume is reduced. The pressure reduces as the temperature reduces. Then, once the temperature reaches freezing, which is the water we dumped it in, the can crushes and the temperature and the pressure returns to 1 atmosphere. The volume stays the same while we freeze, and then the volume suddenly drops as the can is crushed at a constant temperature. Notice, each one looks different. This is a good exercise for your students. All right, this is the very last thing I'm going to talk about with you, the Super Soaker project. This project is a big combination of all things fluids and thermo. Here's the materials. A Super Soaker type squirt gun. Here's what defines a Super Soaker type squirt gun. The gun needs to be able to be pumped up without shooting while the pumping takes place, and then have a trigger so that the gun fires. This gun is broken. Okay, what should be happening, it's cheap crap from Tuesday morning this time. This time it's cheap crap from Tuesday morning. What should have happened was that the squirt gun got filled with pressurized water, and then the water comes out upon pulling the trigger. Well, I can hear the pressurization happening, but this is not working. I'm sorry about that. Okay, but it needs to have both the pump and the trigger. Pump fills with air, trigger shoots the water out. It has to have both those things. What else? Okay, so here is the definition of the Super Soaker type gun. Freeze the video and read it. It's just what I said. Balance. Beaker is optional. Thermometer, stopwatch, meter stick. That's what your students need. They're going to make measurements about the gun before and after firing the gun, and I would do all the actual data taking outside. It's a nice day outside, isn't it? So let's do it. Before shooting the gun, they need to measure the volume of this entire chamber that holds water. Easy. Fill it all the way up with water, and then pour the water into the beaker, or measure the mass before and after it's full of water, and just say that 1 milliliter is the same as 1 gram, which is true for water. Measure the temperature of the surrounding air. Then fill the water chamber with about halfway full of water. They need to know the volume and mass of the partial amount of water they put in the chamber and the volume of the air, which is the rest of the total volume. Okay, they need to know all that. Pump the gun, say 10 times. Shoot the gun, assuming that it works, for about 5 to 10 seconds. Get the following data. The number of pumps, they're writing this down. The time spent shooting the gun, use a stopwatch to get something more precise than 5 to 10 seconds. The height of the water emerging from the gun and the horizontal distance that the water traveled. Sounds like we're going to do projectile motion again, doesn't it? Water will travel lesser and lesser distance as the gun is fired because the pressure is going to get less and less. I want to know the farthest distance that the water went right when you pulled the trigger. When you're done with shooting, get the final mass and volume of the water in the water chamber, so use a beaker or whatever, and then the amount of water that was ejected, that would be the difference between the mass of water before and after, and the final volume of the water, final volume of the air in the water chamber. Well, if you know the final volume of the water, then the rest of the chamber is the final volume of the air. Okay, with all that information, the student is going to do all these things. Holy crap, here it comes. Get the speed that the water comes from the gun. Get the diameter of the small hole that the water comes from. Determine the pressure of the air inside the gun the moment the gun started firing. And determine the number of moles of air that they added during the pumping process. But that's not all. Calculate the total kinetic energy imparted to all the water molecules. Then I tell the students to assume that as the air expanded in the chamber and pushed water out while firing, that was isothermal. Tell me the sign of delta U, Q, and W, delta internal energy, heat, and work for that process. Find the final pressure inside the gun once the trigger is released and the firing is complete. Draw PV, PT, and VT diagrams for the process of shooting the gun, for the water inside the water chamber. Estimate the amount of work done in expanding by the expanding air on the water, and determine the efficiency of the super soaker firing process. Crap, that's a lot, but it brings it all in for them. Here we go. The speed that the water emerges from the gun, use projectile motion. That's the number I got when I shot my gun. I'm going to go through this quickly, so please feel free to pause and look at my work on each slide. That was A. B. Determine the diameter of the small hole that the water comes from. Use continuity. You know the volume of the water that was ejected and the time. So flow rate, volume ejected over time spent shooting equals the area of the little hole, which is what you want, times the velocity that you just calculated in part A. Solve for the area, assume it's a circle, and then use geometry to get the diameter. Part C. Find the absolute pressure of the air in the gun at the instant you pulled the trigger. I use Bernoulli. In the chamber, you have pressure, but you do not have, and we're using absolute pressure here, the height of the chamber, which I have now detached, the height of the chamber and the height of the nozzle are really the same. Okay, I'm dumping out the water here so I don't get myself wet here. Okay, so... all right, so the height of the chamber and the height of the nozzle are the same. So those two height terms cancel out. The speed of the water in the chamber is very slow. So I say that the pressure at the hole is 1 atmosphere. You know the velocity at the hole because you solved for it in part A. Get the pressure in the chamber. That's what I got when I did this. What's the number of moles of air you added? How many moles of air did you add during the pumping process? Well, PV equals nRT becomes delta P times V equals delta nRT. What's delta P? The difference between 1 atmosphere and the pressure you just got after you pumped. Plug that in. What's the volume? The volume of the air in the chamber before you fired. What's T? The temperature outside. Look at the weather. And then I got 0.03 of a mole were added to the firing chamber. Give you a chance to look at it. Part D. Part E. How do you find the total kinetic energy given to all the water molecules? 1/2 mv squared. You got the V of the water coming out. Let's just pretend like it's constant. And the mass of all the water that came out. Yeah, the water slows down a little bit as more comes out. Come on, really? This is an estimate. Okay, what's the sign of delta U, Q, and W, assuming that this is an isothermal process? Work is positive when air is compressed, and work is negative when air expands. The air in the water chamber expands, so W is negative. Okay, delta U is 0 because delta U depends on temperature. Same temperature, U does not change, therefore U is 0. Delta U is 0. If delta U is 0 and W is negative, then Q has to be positive. Heat was actually added to the gas by the surrounding air while the gun was being fired. How do you find the final pressure? I'm going to use a combined gas law. I know the pressure before firing, the volume of the water, of the air before firing, and the volume after firing, and these two temperatures are the same, so knock them out. Do PV equals PV. You know the initial and final air volume. You know the initial air temperature from Bernoulli. Get the final volume, which for me, final pressure, which for me was almost 1 atmosphere. I almost shot it all the way until it stopped working. Okay, here's a pressure volume diagram to scale. To scale. That should curve a little bit, but I can't see the curvature because it's so small. Here's pressure temperature diagram. We go from high pressure to low pressure, but the temperature stays the same. We go from a small volume to a big volume. We go from a small volume to, as the air expands, temperature stays the same. How do you find the work done by the expanding air on the water? You take your PV diagram, you pretend like that's a straight line. I know it curves, but it's close enough to a straight line. And you take the area under, drop down, form a triangle and a rectangle. And if you do that, you should get something like I got, about 7.44 joules. And then how do you find the efficiency? The efficiency is the energy you get out over the energy you put in. What's the energy you get out? The kinetic energy, 1/2 mv squared of all the water that came out. What's the input energy? The energy spent expanding the air in the water chamber. I got 25% efficiency. How about you? It's been fun, folks. I hope this has been helpful. Look for some paperwork that is aligned with these activities and things. You can contact me anytime through Friendly Physics. Go to Friendly Physics. If you have a Facebook account, like, and then send me a message. Send Friendly Physics a message. In the message, please include an email address. I will be more than happy to respond to you by email, and if you ask for anything, or even if you don't ask for resources, you may get them in your email. Hey, here's what I use to help with this. I want to help you as best I can, and I'm going to help you as long as these videos stay with NMSI. All right. Have fun doing AP Physics 2. I think it's a fun class. Have fun.